Hi, this is a geometry video for assignment 13, part 2, the worksheet part of it. The other part, of course, was your chapter 9 test. And we're going to go through this extremely quickly. A whole lot of this, the worksheet's going to be pretty easy. It's not very difficult. It just uses like 4 formulas, and you'll be able to figure it out and use your calculator pretty quickly on it. But I'm going to go over a lot of other information through this video just for your basic knowledge, because with cutting school off early, we're not going to get through everything that I want to get through, so I'm going to try to cram some stuff in here so that you can just have it for your basic knowledge, for your future stuff that you need it for. Diagonal of a polygon, we already talked about diagonals of polygons in the past. All a diagonal is it connects two non-consecutive vertices of some polygon. Triangle, there are no diagonals, so 0 diagonals in a triangle. You can't connect two non-consecutive vertices. For a 4-sided figure, which is a quadrilateral, if I wanted to draw a diagonal, that's a diagonal of it. Now, the reason I'm going over this is because what we're going to do is we're going to figure out this stuff about the interior angles of these polygons, of this quadrilateral and other polygons. And if you look right here, you'll notice that we have 2 triangles when you draw in that one diagonal. Well, each of those triangles, the sum of the interior angles is 180. And this one over here is 180. If we add that up, we get a total of 360. And in any 4-sided figure that you draw, no matter what it looks like, those 4 angles in that 4-sided figure have to add up to be 360 degrees. And that comes from what we just did there by drawing in that one diagonal and making 2 triangles. Now, you could draw in, if we had this pentagon, you draw in the diagonals. Let's go back to this one for a second. We could draw in another diagonal this way. We don't want to do that if we're looking to find the sum of all those interior angles, because now we've introduced new angles there in the middle that would all get added into that. So that wouldn't give us the 360 that we want. So when we're drawing in these diagonals, if we have something like this pentagon, we want to go from one corner, from one vertex. So if we draw that, notice here we got 3 triangles. That's 180, that's 180, that's 180. And any pentagon in the world, if I draw some pentagon, there's 5 angles, and all 5 of those angles are going to add up to 180 plus 180 plus 180, which is 540 degrees. So no matter what the pentagon looks like, all 5 of these angles are always going to add up to 540. And we're going to have a formula that goes along with that. But that's the general idea of where these formulas come from. You could draw in all the diagonals, and that's what this is doing right now, and figure out how many diagonals it has. But again, you notice that you form a whole lot of other little triangles where they have angles inside here that aren't actually part of the original shape. So the formula to find the sum of the interior angles, the inside angles of any convex. Start of the year we talked about convex and concave. Remember, concave is some polygon that looks like this. That's concave. Concave. That's horrible. So that's concave because it's got this angle inside it here. Let me draw a different one. This is concave because it's got this angle in here that is more than 180 degrees. It's got 2 of the sides that sort of point in to the shape. That's concave. We're not going to deal with concave. Everything that we're going to deal with is convex, and convex just means the ones that look normal. So if I was going to do a 5-sided figure, it would look maybe something like that, where all the interior angles are less than 180 degrees. The formula to find the sum of the interior angles, no matter what the shape is n minus 2 times 180. The N stands for the number of sides in the polygon. So if your polygon has 10 sides, then you put 10 in there. And you do 10 minus 2, you get 8. And then you take that 8 times 180. And that's all there is to it. And that tells you what all, and I'm not even going to try to draw a 10-sided figure because I wouldn't do it very well. But that tells you, when you do that math right there, that tells you all 10 angles in that 10-sided figure are going to add up to equal that. Doesn't mean they all have to be the same or anything else. It just means all 10 angles have to add up to that. And no, N here stands for the number of sides. Well, N can also be the number of interior angles, because the number of sides the shape has and the number of interior angles it has is always the same. N could also stand for what we're going to talk about here in a minute, is the number of exterior angles. All three of those, the number of interior angles, the number of exterior angles, and the number of sides are always the same. So if a shape's got 10 sides, then it's got 10 interior angles, and it has 10 exterior angles. Polygon exterior angle theorem. The sum of the exterior angles, this is the easiest thing, and this is your assignment looks like it's long because it's got I think it's 30-some problems on it, but there's at least one of the pages where this right here is going to make it completely easy. The sum of the exterior angles of any convex polygon, one at each vertex, that means one exterior angle at each vertex, is always 360. That's the formula. So the sum of the exterior angles, if they ask you the sum of the exterior angles of a 50-sided polygon, the sum is always 360 degrees. Nothing else. You don't have to do any math. It's always 360. Notice that an interior angle, this is an interior angle right here. And this one out here is an exterior angle. Each interior angle and each exterior angle are always going to be supplementary to each other. They're always going to add up to 180. And the reason it says one at each vertex, because if I use this as my exterior angle, if that's my exterior angle there, well, I could draw another exterior angle that goes right there, but it's at the same vertex. And you'll notice this exterior angle and this exterior angle are actually vertical angles, and they're the same thing. So we don't want two of them there at that one vertex. We only want one at each vertex. So if you got any kind of whatever shape you have, if it's just a four-sided figure or quadrilateral, you want one exterior angle there, one exterior angle there, one exterior angle there, one exterior angle there. So that's an exterior angle, exterior angle, exterior angle, exterior angle. You don't want extra exterior angles. You don't want to extend this side out and make another exterior angle over here. You want one at each corner, one at each vertex. Remember, equilateral polygons, we talked about this earlier this year. Equilateral polygons, all the sides are always congruent. So if it's equilateral, like if it's a stop sign, it's an octagon, equilateral octagon, because all the sides are always congruent. If it's equiangular, all the angles are congruent. If it's both of these, equilateral and equiangular, then it's called a regular polygon. We talked about that earlier this year. Regular polygons, all the sides and all the angles are congruent. Triangles, if you have a triangle, when we had a triangle that was equilateral, it also had to be equiangular. But a triangle is the only shape, the only polygon that works for. If you have a four-sided figure that's equilateral, could look like this, and that doesn't mean it's equiangular. This is a rhombus, and we'll talk about it here in a minute. If we have a four-sided figure that's equiangular, it could look like this. It could just be a rectangle. but that doesn't mean it's equilateral. And that works for all the other polygons too. Home plate on a softball field is equilateral. All these sides are the same length, but all these angles aren't the same measure. So it's equilateral, but it's not equiangular. The only polygon that has to be both, if it's one, then it has to be the other, is a triangle. Now there are polygons that are both equilateral and equiangular, like a square. Square, all the sides are congruent and all the angles are congruent. So it's called a regular polygon, or if it was a square, it could be called a regular quadrilateral because it's got 4 sides. If a shape is regular or equiangular and we want to find each interior angle, then we just use this formula, n minus 2 times 180. So we put in number of sides for n, figure out that, times it by 180, get that answer. That tells us the sum of all the interior angles. And then since we know it's regular or equiangular, either one of them, we just divide by how many angles there are or how many sides there are, and that's going to tell us each interior angle measure. It's going to tell you each angle separately. For each exterior angle, formula is pretty easy because we know the sum of the exterior angles always has to be 360. So we just take, if it's a regular or equiangular polygon, then we just take that 360 and we divide by the number of sides or the number of angles. And that's going to give us each exterior angle. I would use this formula a whole lot more than I ever use this one, because if you do this, if you know a shape is got 4 sides and you take 360 divided by 4, you get 90. Let's do something different. If you know a shape's got 5 sides, you take 360 and you divide it by 5, and you get 72. That means each exterior angle is 72 degrees. Well, whatever shape I'm looking at, however many sides it has, if each exterior angle, that's an exterior angle there, is 72 degrees, then we can find each interior angle just by subtracting that from 180 because they have to be supplementary. So we just do 180 minus 72, which is 108. So we can find this by using this. And that's a little easier sometimes just to do this formula. This slide just gives you all 4 formulas. For all polygons, if you're looking for the sum, then use, if you're looking for the sum of the interior angles, use this formula. If you're looking for the sum of the exterior angles, it's always 360. If you know the polygon is regular or equiangular, then we use this formula to find each interior angle. So each one separately, that means all of them are going to be the same because it was regular. And we use this formula to find each exterior angle because all of them are going to be the same. So if I have a pentagon, if I could draw a regular pentagon, if we know that that's regular, and I want to find each of these interior angles, then I can just do 5 minus 2 times 180. 5 minus 2 is 3. I take 3 times 180, and I end up with 540. So all 5 of these angles add up to 540 degrees. This is the part that the homework's going to cover. All 5 of those add up to 540. If that's all they wanted was the sum of them, then that's all you do. If we know it's regular, so all these angles are congruent to each other, then I take that 540 and I divide by the number of sides, which is 5, and I come up with 108. So that angle right there is 108. That angle is 108. That angle is 108. That angle is 108. This angle is 108. Ignore that. So all those angles are 180 degrees. Then if I want to find each exterior angle, I know that it has 5 exterior angles. And they're all going to be the same because it's regular. I could just say these two together have to add up to 180 and get 72 there. Or I could use this formula and take 360 divided by 5, and that's still going to give me 72. So every one of these exterior angles is 72 degrees. Ignore that. So 4 different formulas. If you're just looking for the sum of the interior angles, use that formula. If you're looking for the sum of the exterior angles, it's always 360. If it's a regular polygon and you're looking for each interior angle, use that formula. If it's regular and you're looking for each exterior angle, that's 360. That's the main part of this whole lesson. Here's a chart that could help you. We did this part of the chart earlier this year, where we did the names and the number of sides. Remember, 3-sided is a triangle, 4-sided is a quadrilateral, 5-sided is a pentagon, 6-sided hexagon, 7-sided septagon, or heptagon. Either one of those names. I only put one of them on here this time. 8-sided is octagon, 9-sided is nonagon, 10-sided is a decagon, 12-sided is a dodecagon. If it's not on that list, if it's not one of those, then when we name it, we just use the number of sides and we call it with that number of sides. So if it's got 25 sides, then we just say a 25-gon. We talked about all that earlier this year. Again, N stands for the number of sides. So if you wanted to call this shape a 5-gon, you could. I won't accept that on a test or anything like that, but because I would want the proper name, which is a pentagon, but it could be called a 5-gon. So on, so on, so on. The sum of the interior angles is in this column right here. If it's on that list and you know it's 5-sided, and you want the sum of the interior angles, then you just have to write down 540. If you can memorize this list, that's great. If not, then you're going to have to use this formula each time for each different polygon. Sum of the exterior angles, notice right here, real difficult. Hopefully you can memorize that list. Sum of the exterior angles is always 360 degrees. No matter what the shape is, the sum of the exterior angles is always 360. These last two, if the shape is regular or equiangular, then this is telling us each interior angle and each exterior angle. So, and we already know this one for a triangle. If it's regular, each interior angle has to be 60 degrees. Quadrilateral, each interior angle, if it's regular, that means it's got to be a square. Each interior angle is a right angle or 90 degrees. And then so on all the way down through here. And you can notice on some of these, this is why we use pentagons and hexagons quite often. This is why we don't use septagons real often, because the angles don't come out all nice and even. Find each exterior angle. If it's, let's say, if you got a 25-gon, then all you're going to do is in place of N right here, you're going to put in 25. In place of N right here, you're going to put in 25. Do 25 minus 2 times 180. Get that answer, then divide that answer by 25. That's going to tell you what the measure of each angle is in a 25-sided figure. Here, to find each exterior angle, we just put 25 in there, if that's what we're doing. If it's any other shape, you know, if it's got 30 sides, whatever, then you put 30 in for N. You just take 360 divided by 25, that's going to tell you each exterior angle. So those are your 4 formulas down here at the bottom. Those are the 4 things that we're going to use on the assignment. Now, these are all quadrilaterals, and I'm going to go through these extremely quickly because the assignment doesn't really have anything to do with this, and and you may have seen all of this before, but I want to go back over it with you. And I'll probably draw a picture with each one, and there'll be an extra set of notes attached that you can look at to just for your own basic knowledge. A parallelogram, most of the time a parallelogram looks something like this. In a parallelogram, both pairs of opposite sides are parallel. So those two are parallel, those two are parallel. Both pairs of opposite sides are congruent, so this is congruent to that, this side's congruent to that. Opposite angles are congruent. Opposite angles means this angle and this angle and this angle are congruent. Consecutive angles are supplementary. If I label this A, B, C, and D, any angles that go right next to each other have to add up to 180. That's what supplementary means. The diagonals, if I were to draw, I'm going to draw another one down here. If I were to draw these diagonals in, my shape's not very good. These diagonals bisect each other, so this segment's congruent to that segment's congruent to that segment. And the sum of the interior angles, which we just talked about because it's a four-sided figure, is always 360 degrees. So this angle, this angle, this angle, this angle, all added up have to be 360. That's a parallelogram. Rectangles. A rectangle is a parallelogram, so all those properties that I just went over for a parallelogram also fit for a rectangle. So if I draw a rectangle here, all the properties that we just went over fit for that. I'm not going to go back through them all. The new properties for a rectangle that didn't work for all parallelograms, it has 4 right angles. That's the main property for a rectangle. It has 4 right angles. And then the diagonals are also congruent. So the length from here to there and the length from here to there are exactly the same. So we know that they bisect each other, so that means these 4 little segments in here, all 4 are congruent to each other, if that shape's a rectangle. If you want to prove something is a rectangle, first you prove it's a parallelogram, then you prove it's got a right angle, then it has to be a rectangle. A second way to prove it's a rectangle, prove it's a parallelogram, and show that the diagonals are the same length. The 2 diagonals are the same length, and then you could prove it's a rectangle. Some of you are probably happy you see this prove word, because that means we're not going to have to do all those 2-column proofs for this stuff. Rhombus. Rhombus is another quadrilateral, another 4-sided figure. It's still a parallelogram, so it's got all the properties of a parallelogram. The main property of a rhombus is it has 4 congruent sides. All 4 sides are the same. 2 other new properties that weren't properties of a rectangle or a parallelogram. If I draw in this diagonal, it bisects that angle, and it bisects that angle. And all 4 of these angles are the same. Same thing going the other way. This angle and this angle are congruent, and they're congruent to these 2 angles also. And then the last property, when you draw in these 2 diagonals, these angles right here in the middle, which is important for what we just got done doing, are all right angles. That makes this a right triangle, makes this a right triangle, makes this a right triangle, makes this a right triangle. So we could use Pythagorean's theorem, all the trig ratios, to find a bunch of different things on any of those 4 triangles, because they're all right triangles. Prove it's a rhombus, prove it's a parallelogram, and then just prove 2 consecutive sides. 2 sides that are hooked to each other are congruent, then it's got to be a rhombus. Prove it's a parallelogram where the diagonals are perpendicular. That means prove that there's a right angle in here. A square. Square is a parallelogram, so it's got all the properties of a parallelogram. I'm not going to go back over them all. It's got all the properties of a rectangle, and it's got all the properties of a rhombus. So it's got all those properties that I just covered for those 3 other shapes. A square really doesn't have any of its own properties. The one thing I will say about a square is if you draw in this diagonal, We know this is a right angle, and in a rhombus, that diagonal bisects each angle, and if this angle down here was 90 degrees, that means each one of these is 45. Well, then what we have is each one of these two triangles is a 45, 45, 90 triangle. And we talked about that a little bit when we talked about the 45, 45, 90 triangles. To prove something's a square, prove it's a parallelogram, then prove it's a rectangle, maybe show that it has a right angle. And I spelled prove wrong here. Prove it's a rhombus, and if it's all three of those things, then the shape is a square. Trapezoid. Trapezoid normally looks like this. It doesn't have to. Properties of a trapezoid. Two of the sides, which are called the bases, are parallel to each other. So it's got one pair of parallel sides, then the other two sides are not parallel. The angles surrounding the leg are supplementary. Each of these two sides, that's a leg, this is a base, and this is a base. They're not the same, and the legs don't have to be the same, so we'll say leg 1, base 1, leg 2, base 2. They don't necessarily have to be the same, but the angles surrounding one of those legs, each one of them, have to be supplementary. They have to add up to 180. To prove something's a parallelogram, all you got to do is show that one pair of sides is parallel. If it's an isosceles trapezoid, then it's got a few more, and even though my first one looked like an isosceles trapezoid, in an isosceles trapezoid, what's new about it is the legs have to be congruent to each other. Just like an isosceles triangle, where the legs are congruent, an isosceles trapezoid, the legs have to be congruent. If those legs are congruent, this angle is always congruent to this angle is always congruent to that angle. That doesn't work for every trapezoid, only works for isosceles trapezoids. To prove it's a trapezoid, we have all that, or I should say, prove it is an isosceles trapezoid. We could do that. I'm not going to go through all that. Kite's another four-sided figure, another quadrilateral. Kite looks like this. And the definition of a kite is it's got two pairs of disjoint consecutive sides that are congruent. So, and all that means is that these two sides are congruent, these two sides are congruent. One pair of opposite angles are congruent. You just have to figure out when you're looking at this kite, hey, it's going to be this angle and this angle. This angle and this angle are not congruent to each other. Diagonals are perpendicular. If we draw in the diagonals here, they're going to form right angles in the middle. So again, we have four right triangles there. That's what this does. So all those in there, those four angles in the middle are all right angles. One of the diagonals bisects the other. If you look at this, it looks like this diagonal right here is being, should put a third mark on there, is being bisected. And you notice this diagonal is not being bisected because one part's longer than the other. One of the diagonals bisects the two angles. This diagonal actually bisects. So these two angles are congruent. These two angles are congruent. Kites are sort of hard because it works for everything works for like half the shape. Sum of all the angles, sum of all the interior angles is 360, just like every other four-sided figure that we've dealt with all the way through here. This is sort of a hierarchy or a tree diagram for this. You got a four-sided figure, that's all it has to be a quadrilateral. It's got four sides. This is the new tree diagram. They want you go to quadrilateral, then you check to see if it's a trapezoid, then you check to see if it's a parallelogram, and and then maybe check, see if it's an isosceles trapezoid, if it's not a parallelogram. If it is a parallelogram, then you check, see if it's a rectangle. And if it's a rectangle, then you also check, see if it's a rhombus, because if it's a rectangle and a rhombus, then that tells us it's a square. So that's just how we do it to check through something. The old diagram looks something more like this, quadrilateral, and I'm not going to write out all these names, but I'll write out quadrilateral here. Quadrilateral, if it's quadrilateral, then you check, see if it's a parallelogram. If it's not a parallelogram, then we check, see if it's a trapezoid. Some of the new books, it's sort of a thing that they've changed in math, they put trapezoid over here in the hierarchy with the some of the other four-sided figures. The old stuff, trapezoid was sort of by itself. If it wasn't either one of those two, then you check to see if it was a kite. If it was a trapezoid, you check to see if it was isosceles or not. Parallelogram, if it did happen to be a parallelogram, then you keep going down this way and you check to see if it's a rectangle. If it is a rectangle, then you check to see if it's a rhombus. If it's not a rhombus but it's a rectangle, then you stop right there and you call it a rectangle. If it's both of these, then the very best name to give it is a square. So that's if we were trying to prove some shape of something. First thing we look at, see if it's a quadrilateral, if it's got four sides. Then we check to see if it's a parallelogram, if opposite sides are parallel or whatever else we might be able to prove. If it's not a parallelogram, then we check trapezoid and kite, see if it's one of them to give it a name. If it is a parallelogram, then we continue on down, check see if it's a rectangle. If it's not a rectangle, we check see if it's a rhombus. If it's not a rhombus, then the best name we can give it would be a parallelogram. If it is a rectangle and it is a rhombus, then the best name we can give it is all the way down here, square. And it's just a hierarchy to show what the very best name for that certain four-sided figure is. Again, these are the four formulas. Make sure you know those. That's what you're going to use on the assignment. This is the table again. Would help you if you know that you're dealing with a hexagon, then you know the sum of the interior angles is 720, the sum of the exterior angles is 360. If it's regular, each interior angle is 120 and each exterior angle is 60, and you could just use that chart to fill in some of your answers on the assignment. Don't do that.